Here's our next example of finding a solution to a differential equation using series. Suppose we have the differential equation xy double prime plus y prime minus xy equals 0. So the approach is to begin in step 1 by assuming that y is a series. So it's the sum going from 0 to infinity of some coefficients an, which I wish I knew, because if I did know these coefficients an, then I'd be done with the problem. Then I'm going to plug in this assumption into my differential equation. So we've seen in the past couple of examples how to take derivatives and second derivatives. I'm just going to plug that in now into my differential equation. So I have x times the second derivative, which is the sum going from 0 to infinity, an times n minus 1, x to the n minus 2. The derivative is the sum going from 0 to infinity of an x to the n minus 1. And the sum itself is the sum going from 0 to infinity, an x to the n. All of that should equal 0. Now, I'd like to compare the coefficients of x to the n on both sides of this equation. In preparation for that, I'm going to make every exponent be x to the n power. So if you notice here, I have an x in front times x to the n minus 2. So the first sum, I'm going to shift by 1. I will find the sum going from 0 to infinity of an plus 1, n plus 1 times n, x to the n. So what I just did there was shifted all the indices by 1 because I have an x to the n minus 1 power. So I want to increase n by 1 to get x to the n. If you're ever confused about this shifting of the indexing of the sum, just plug in the first couple values of n into both series and check that you actually did do the right calculation. I do a similar calculation for the middle term. So the middle term will be the sum going from 0 to infinity, an plus 1, n plus 1, x to the n. Now for this term, I have an x to the n plus 1 power, so I want to shift everything down. This will be the sum of an minus 1 x to the n, but I'm going to start the sum at 1. You could check that this is correct because if I plug in n equals 0 into this term, I get a0 x to the first. If I plug in n equals 1, the first term in this series is a0 x to the first, so it matches. The third step in my procedure to find a series solution involves comparing the coefficients of x to the n. Now, if n is 0, I have the first two terms in my sum. And if n is equal to 1 or beyond, all three series kick in because this sum starts at 1. So I'll break that into two cases. When n is equal to 0, the coefficients of x to the n on both sides, the coefficient of x to the 0, I should say, gives me a1 times 1 times 0 plus a1 times 1 should equal 0. Again, I looked at the coefficients in the first two sums. The third one hasn't kicked in yet when n is 0 because there is no coefficient of x to the 0 in the third term. So what I find is that a1 is equal to 0. Now, when n is bigger than or equal to 1, we have all three terms kick in. I have an plus 1 times n plus 1 times n plus an plus 1 n plus 1 minus an minus 1 is equal to 0. I could take this relationship and I can solve. It'll turn out that an plus 1 is none other than an minus 1 over n plus 1 squared. So this is my relationship between an plus 1 and smaller values of the same sequence, an. I'm going to come up here and draw a table with values of n and this relationship. An plus 1 is equal to an minus 1 over n plus 1 squared. So this relationship really starts kicking in when n is 1. So I'm not going to plug in 0 here. If I did plug in 0, and I've seen students erroneously do that in my past, then I would get an a negative 1 term. That doesn't make sense. So this doesn't even make sense until n is 1 and beyond. So if n is 1, this relationship says a2 is a0 over 2 squared. If n is 2, I get a3 is equal to a1 over 3 squared, but we already determined a1 was equal to 0, so this is just 0. n equals 3 gives me a4 is a2 over 4 squared, but I already found a2 2 rows above. That's a0 over 2 squared. So this is a0 over 4 squared times 2 squared. The a5 term, I hope you could see, would involve the a3 term, which also involves the a1 term, which is 0. So in this example, you will only get non-zero terms for the even coefficients of an. So I get to write down my final answer in step 4. So my answer is y is a0 plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth, and so on. And now I know information about these coefficients. So I don't know anything about a0, but I do know a1 is 0, so that term's gone. All the odd coefficients gone. a2 is equal to a0 over 2 squared, so that's my coefficient of x squared. My coefficient of x to the fourth is a0 over 2 squared times 4 squared, x to the fourth, and so on. This is a0 times 1 plus x squared over 2 squared plus x to the fourth over 2 squared times 4 squared plus x to the sixth over 2 squared, 4 squared, 6 squared. And this goes on forever. There is my solution. However, in this example, I'm a little bit disappointed because I have a second-order differential equation. It's linear. That means I expect two linearly independent, two different solutions to my differential equation. But I only got one. So the method of series solutions might give you only one solution. Luckily, we have a technique, reduction of order, that allows us to find a second solution given the first. Okay, there's series solution example 4. Wonderful.